Hello, and welcome to this Tobii Pro webinar on Understanding the Screen, what you need to know for sizing stimuli and analyzing gaze data. I'm Wilkie Wong, Director of Knowledge Services at Tobii Pro, and I'll be presenting the webinar today. Have you ever wondered, how big should I make my stimulus? How far apart should I place things on the screen? How large of a display screen should I use? How big should I make the AOIs? When should I be working in pixels, centimeters, and degrees of visual angle? Well, if you've asked yourselves any of these questions, then this webinar is for you. There are two major learning objectives for this webinar. The first is to help you understand the relationship between pixel dimensions, which relates to image space, screen size, which relates to physical space, and viewing angles, which relate to visual space. The second major learning objective is to understand how to properly size your stimuli and AOIs, or areas of interest, for a given display, taking into account the limitations of the human visual field and the eye tracker. Ultimately, so you can do great eye tracking research. Let's unpack the first objective a little bit more, understanding space. Why do we need to do so? Because there are in fact three spatial systems at play in any screen-based eye tracking study. And we design in one, present in another, and analyze in yet a third. So let's get our ducks in a row and do a little exploration of these three spatial systems and what that means, starting with the design process and the considerations that are involved in rational design of your eye tracking stimuli, all the way through to the analysis stage, where you might be setting up areas of interest to get the best gauge on visual behavior on that stimulus. Let's start by taking a look at the three D spaces of eye tracking. Pixel space is the first space, and pixel space relates to the virtual world and the world of design. Screen space relates to the physical world, the world of the display of this design. And third, angular space relates to the visual world and the description of the motions and actions and behaviors in that world.
Now let's just spend a moment to consider not the 3D spaces themselves, but the intersection between these spaces. At the intersection between pixel space and angular space are the initial considerations and questions about how we want the visual stimulus to be perceived and reacted to in terms of the behavior of the eyes. At the intersection between pixel space and screen space arise issues and considerations relating to the design and rendering of the stimulus. And in that case, it's not just sufficient to design an image per se with some fixed pixel dimensions. You need to do so keeping in mind the size and resolution and the characteristics of the display upon which the stimulus is actually going to be rendered. And finally, the intersection between angular space and screen space is where we will seek to describe the visual behavior that we capture in response to actual physical representations of stimulus in the real world. And right here at the center is where we endeavor to be, and that is a clear, expert, and practical application of the principles and considerations in each of these spaces and their intersections. Let's start by taking a look at pixel space, the first of the spaces, and it's the space involved in designing. It's important to understand that pixel space is really an abstract space. It's image-based, and it doesn't bear any necessary relationship with the real world. So I could say that this element here is 1 pixel in extent, and then 3 and 4 and 5 and so on. Alternatively, I could say that this bar down here, which has the same visual extent, consists of 100 pixels, and that would be perfectly fine. One thing to keep in mind is that Tobii Studio doesn't really work in vector formats. So formats such as used by Adobe Illustrator or Encapsulated PostScript or Corel Draw or drawing programs in general are generally not supported in Tobii Studio. So pixel space is the abstract space involved in the design stage.
The second D is screen space, and that is the space for displaying. And since it's a physical space, there is a real unit of measure. And generally it's an inch or a centimeter or something of that nature. And screen space can be thought of as the canvas upon which abstract pixels are rendered and brought into the real world. So for example, in years past, a 15-inch diagonal monitor could have rendered 640 by 480 pixels. A modern monitor, such as the one found on the TX300, could render 1920 by 1080 pixels across a screen that's 24 inches diagonal. And the modern state-of-the-art would be something like this 32-inch diagonal 4K display, which has significantly more pixels than the Full HD. It's important to note that Tobii eye trackers, as well as any monitor, has characteristics that a researcher needs to understand and know how to work with. And let's take a look at a couple of these display characteristics for Tobii eye trackers, like the T120 and T60, T60XL, and the TX300. The X and X2 series are sort of bring your own monitors to the party. So what these specifications turn out to be is entirely dependent on the display you choose. But these systems with integrated displays have, of course, pixel measurements, of course, and active screen measurements, here delivered in terms of inches. The two important, this is the important number, pixels per inch. That's the pixel density, and you can see that in our stock eye trackers, generally it's about 94 or 95 pixels per inch, with an average pixel size of about 1/4 of a millimeter, and a typical foveal extent or central high-resolution vision of 1 degree at 64 centimeters viewing distance, about 25 inches, translating to about 45 pixels. At this point, it's also useful to mention at least the coordinates, one of the multiple coordinate systems that Tobii eye trackers use. And this is a schematic of the active display coordinate system. And in this coordinate system, which relates to the monitor upon which the stimulus is displayed, you have up here in the upper corner the origin, which is 0, 0, and then all the way down at the lower right would be whatever the maximum X and Y are in terms of pixel extent for that monitor. In terms of software that you can use to create your images for your eye tracking study, you're not really very restricted, as long as you choose something that works in bitmap or pixel format. And that could include things like Microsoft Paint, Photoshop, Graphic Inverter, or GIMP. The third space that we need to discuss is angular space, and the third D that's associated with it is describing. And in this angular space, the unit of measure is a calculated geometric measure, the degree. And how gaze measures are calculated and how human visual behavior is analyzed on a visual display is calculated in terms of degrees. In fact, the internal calculations for Tobii eye tracking systems are executed in terms of visual angle, in terms of degrees. So here you can see from a published paper about the 3D eye tracking model, degrees of measure and angular extent are really fundamental to the process of calculating gaze points and visual axes. Okay? And if you are familiar with the Tobii calibration verification tool, which is a standalone utility that allows you to assess the accuracy of a person tracking to target. The results are reported in root mean square degrees of visual angle. Here you see it for a pretty good result for left and right eyes. And if you're a researcher in fields that are interested in saccade metrics or saccade measures, then you'll already be familiar with reporting results in terms of degrees. For example, saccade amplitude and saccade amplitude distribution are reported in degrees of visual angle. And that brings us to a discussion that many researchers will face, and that is, well, how do we size stimuli appropriately? The touchstone that you want to focus on is maintaining constant visual size. And this is particularly true if you're talking about a physical object, such as a large nutcracker that is typically seen at a large distance, at some distance, and you want to test looking to it perhaps by displaying it on your TX300 or T60XL. Well, if the nutcracker is larger than the vertical dimension of the monitor, then you can't show it life size. So how do you deal with that? Well, the principle here is that if you have a nutcracker of vertical dimension y, let's say, and it's typically viewed at a distance x, and you want to translate that for the screen, what you need to do is maintain the visual angle occupied by that nutcracker, so that when you display it at a distance of x prime, and let's call that this plane right here, the plane of the display of your eye tracker, you can scale it to a height of y prime, and in doing so maintain the exact same visual angle coverage, presumably to deliver the same visual weight and elicit the same elicit naturalistic behavior. Okay? And calculating these dimensions are not at all difficult. It basically boils down to a ratio. So the ratio of the distances, your x and y distance, your real and intended, can then be used to calculate the y distance given that x prime is going to be somewhere between, say, 55 and 75 centimeters, typical viewing distance from the screen. Okay, so as an example, you can have a 20-inch nutcracker viewed at a distance of 50 inches, but now you want to show it on a screen that's 25 inches away. That means the nutcracker must scale to 1/2 or 10 inches. So to recap, the three 3Ds in terms of spaces for eye tracking are: the first D, designing your study in pixel space, while keeping in mind how the stimuli will display in the screen or physical space to elicit behaviors that you can describe or measure in angular space to allow you to analyze the behaviors for whatever construct you're looking to investigate. So the 3Ds again are design, display, and describe, and the related spaces are pixel space, which is the virtual space, screen and physical space, which is the rendering space, and angular space, which is the description of eye movement that's independent of distance. So how do we put that rubber to the road? In the next section here, we're going to examine a model workflow, which consists of three things that we're going to discuss. First would be basic eye tracking design considerations. Second would be design and execution of a study. And third would be the analysis and interpretation. Let's take a look at some of the basic considerations. This includes thinking about the research question. That involves the visual targets that you're going to be employing, the type of behaviors that you're going after, and the scope and scale of the study itself. Second point would be measures and statistics. What sort of analyses, tests, metrics, or inferences you want to make based on the data. And the third point is experimental design. So questions about significance and power as they relate to sample size, perhaps. So these are really all considerations that are basic to any empirical study. However, there is a visual component that we'll need to think about now, since eye tracking involves visual paradigms. And we're going to keep in mind those basic considerations. But remember that we have some other factors that reflect on and limit, in some cases, what we can do in our studies. So, for example, two things that come to mind immediately are that the pupil center corneal reflection technique that Tobii eye tracker and many eye tracking systems employ has a typical accuracy of 1/2 to 1 degree in a real setting. Okay? And what that means is 0.6 to 1.2 centimeters or 1 degree of accuracy at a distance of about 25 inches. So that's really your touchstone for 1/2 to 1 degree of typical accuracy at distance. The second point is to understand that human perceptual span is strongly stimulus and task dependent, which means that whether you're running a reading study or a visual study that involves scene, maybe foreground and background, whether you're looking at facial images images or cartoons or representations, or in the case of this on the right, which is sort of like a visual pop-out paradigm, the perceptual span would be expected to change and react to the stimulus and task.
Now, in addition to basic hardware and stimulus concerns, we also have to be mindful of the fact that visual responsivity varies over the field of view. What exactly does that mean? Let me pull out my laser pointer here. What it means is that when we are looking straight ahead, on axis, projecting directly out from our face, we can discern fine details with good precision. However, as we move out towards the periphery of the visual field, we quite rapidly lose sensitivity to fine detail, ultimately gross detail, and then at the far periphery, we're primarily sensitive to color, and then ultimately motion and contrast. So what can be discerned varies as a function of its location in our visual field. Not only that, but the physiology of the human visual system has characteristics that need to be considered, and one of these is the visual acuity. If 0 degrees is considered the visual axis as it projects out from the fovea, which is at the very center of the macula, the high spatial resolution region of our retina, here we define that as 1, or peak visual acuity, and we see that drops off quite precipitously off to the edges. So the point of this slide is to show that not only can what the system is able to discern varies in terms of its location in the visual field, but the acuity with which we can discern it also varies as eccentricity increases, or as we move further and further from on axis.
And let's see how that manifests in terms of the concept to design translation. Let's take the example of a face stimulus. It's pretty straightforward. And even in something as seemingly simple as a face image, there are multiple considerations. So, for example, how small or large should I make it? And how far or near can and should the elements be that are within the actual stimulus itself? And if you're working with two stimuli on the same image or the same presentation, you have considerations to think of as well. One of those would be how near or how far I can place things, and also considerations of now intra-stimulus distance and spacing relative to inter spacing. And interspacing means the considerations of where the center of the images are, as well as the regions of closest approach, which in this display are the ears. Okay. So let's take a look at one of two cases. In one case, you can control the design, which means you have the latitude, you're the creator, you can make the stimulus what you want it to be. So in this case, wherever possible, you want to make the stimulus elements or text large and well separated. And what that means generally is building in 1 degree or about half an inch or 1.2 centimeters of visual insulation around the designed areas of interest. That means if you want, well, we'll take an example. We'll take an example of that in the next slide. And as always, it's always meaningful to test the setup on target populations, whether it's general population or children or older folks. You want to test it for accuracy and precision of targeting, especially at your regions of interest.
Now let's see how some of these considerations play out in terms of a simple two-element stimulus display. Let me fire up my laser pointer. Okay, so in this case we have a display which includes two faces, one on the left and one on the right. What we want to ensure is that there is sufficient separation between these so that we can differentiate looking and assign gaze appropriately as to being on the first face or the left face relative to the right face. And this means that wherever possible, we'd like to insert approximately a degree of visual separation. So if this arrow represents approximately a degree of visual angle, we can, if the paradigm permits, provide that amount of space around each of the individual faces or sub-elements on this array. And if the paradigm permits, meaning that it's not affected or visual behavior is not negatively influenced by having to look from one face and then traverse the screen to look at the other face, then it wouldn't hurt at all to have an additional 1 degree separating the buffer zones around the individual faces. So again, when you have a freedom to design your stimulus or stimulus array, then you can place them where you would like to place them within reason, and this will help your analysis on the back end, which is going to involve testifying to really the confidence that gaze on one face is not really intended for features of gaze on the other face. Another example where one needs to be attentive to inter-element spacing might be in reading research, for example. In this case, the individual lines of text would be the elements that a researcher might be interested in separating out in terms of the analysis. So what we see here, it would be, let's say in the upper case, the upper paragraph, this is the same text exactly. In the upper piece of text where the line spacing is approximately 1.1, you can see that the AOIs to capture the fixations on the line of text are pretty well close together. So there is the danger that gaze intended for, say, the word cup, let's see here, well, maybe brown or over, could be actually intended for a neighboring line or an adjacent line, and not the actual line where the AOI is drawn around. However, if you can increase the line spacing and your paradigm and your technique allows you to do so, being able to space the AOIs of this line versus the second and third lines out allows you to separate out the fixations, provide a little bit of spacing between the lines so that you can have greater confidence that a fixation registered in a given AOI actually does belong to the text on that line.
And in addition to interspacing considerations, there are intraspacing considerations. And again, using the same 46 pixel, 1 degree, half an inch, 1.2 centimeter spacing at a typical viewing distance of 64 centimeters. Your considerations have to do with, well, the eye zone versus the mouth zone. Maybe applying the 1 degree spacing around the eye to making sure that your stimulus provides for that. From the mouth to the edge of this anticipated area of interest. And maybe you also want to separate viewing, maybe you want to be able to separate viewing between the eyes, so left eye versus right eye. In that case, you'd want to be attentive to making sure that there's some visual insulation between the elements on the face. Now let's consider the situation when you can't control the design. And that might be the case if the object of study is a piece of commercial packaging or ad material, or a website that's not under your control. What can you do in this case? Well, you can certainly review the recordings and look for outliers that might strongly skew results, and also be attentive to Vergence issues, which we'll describe in the next slide. You also want to be aware of AOI overlap, and this could result in inflated fixation and visit counts, false transitions between areas of interest, and could be problematic in your analysis. Additionally, you may find yourself having to focus your analysis on larger elements and assemblies rather than the more granular details, simply because they may be too close together for you to separate in terms of individual AOIs. So you should also try to add a degree of visual insulation around constructed areas of interest wherever possible, and really this is more likely if you have isolated elements and targets with stuff around it that you're generally not that interested in looking at. Hopefully the important areas will not be very closely abutted to each other. And the final point is to make sure that you test the setup on a target population for accuracy and precision, especially at the regions of the screen where you may expect the important action to transpire. So what exactly are Vergence effects? Let's take a look at that in a little bit of detail. You can think of Vergence as basically the ability of the eye to accommodate for whether what you're looking at is close or far. And that means either bringing the visual axes or the eye lines together for something that's near, versus something that's far, where the eye lines will separate out into space. So let's take a look at an example of that. So why do we want to be mindful of Vergence effects? Because Vergence effects, if you're not aware of them or don't treat them properly in the data, can appear as data offsets. So let's take a look at this example here. And what I've got is a 9-point target, a 3x3 grid, and these are fixations to those targets. Obviously, it looks pretty bad, but what exactly is going on here? Is there a problem with the equipment? Is there a problem with the subject? It's sort of hard to say. It is worthwhile noting that the default setting for Tobii eye trackers is to take the average of left and right eyes. And in this case, if we take a look at the left and right eyes separately, then the real cause of this particular situation becomes clear. Here you see the left eye data, and the left eye data is even further out than the average of the both eyes, which makes sense. So that means that the right eye is likely to be on this side of the average, and down here where they're pretty close together, the right eye is likely to be close. So in this case, what we see is the average value is off target, but it seems to be strongly driven by the left eye. Let's take a look at the right eye. And there you go. So in this case, the right eye is tracking true. It's targeting properly, and the left eye is varying in terms of its Vergence and targeting to the targets, to the visual targets, depending on the position on the targeting grid or in the screen. And this suggests that you need to be careful about what appear to be offsets, because they may in fact have to do with dominant or non-dominant eyes behaving differently during a given task. So, staying on the subject of designing stimuli, we're going to make a segue into the analysis of visual behavior on the stimuli. So let's take time out for a short statistics sidebar and take a look at two topics. The two topics of interest here are selectivity and sensitivity. And selectivity can be written as 1 minus alpha, the type 1 error, or false positive rate. And sensitivity can be written as 1 minus beta, or the type 2 error, or false negative rate. And discussions of the finer details of selectivity and sensitivity and beta and alpha error aside, the straightforward way to think about this in terms of eye tracking is as follows. Selectivity can be described as the chance of excluding all non-applicable gaze. And sensitivity can be described as the chance of including all applicable gaze. And let's explore this by way of an example. So we have two targets, as evidenced by this scattering of gaze points. So let's consider these as gaze points, and this scattering of gaze points. Now, this is simply looking to targets, and we might presume that, hey, maybe the target is somewhere here and maybe somewhere here. That's where the centroid appears to be. Let's say that we want to analyze looking on the basis of selectivity. So, in designing our areas of interest, we might set up an AOI like this. It's selective biased in the sense that it's very, very important for me to not include any looking that was intended for the right side target. And in order to do that, I'm willing to give up a little bit of looking on the periphery of the left side target. Okay. Conversely, you could design this AOI to bias towards sensitivity, which means I want to capture all of the looking to the left side target, and I'm willing to accept the occasional stray gaze point or fixation from the right side target. Now, whether you bias towards selectivity or sensitivity in the design of your AOIs really depends on a couple of things. One of which might be whether it is more critical or worse if you underestimate a finding versus overestimate a finding. And there are also considerations of the sidedness of the metrics that you're analyzing. So think a little bit about the risk involved in over or underestimating the actual or capturing the gaze data to a particular test or target, and that should guide your bias towards selectivity and sensitivity if indeed you have to make a decision. And generally we do at least have to be mindful of this, even if we have full and complete control over the design and analysis. And let's see how this might manifest in an actual example. So let's take this example of a website and show what the selective and sensitive areas of interest might look like. On this side, on the free panel, is a boundary for what I would propose to be a selective AOI. And that means that, hey, listen, I really want to just capture looking to the central region of this particular element. And I'm willing to exclude stuff that's out near the edges. And alternatively, so I would try to inject a 1 degree visual boundary there, if at all possible. In contrast, on the premium panel, I might want to capture all looking that's in this vicinity, that's targeted towards any of the things that's on this pane. And you can see that it is a little different from the free panel. There's this little badge up here that calls out the price, and there's also a call to action, an action item here that is a buy now button that you would click on to proceed to register. So I really want to capture looking to everything in total on the stimulus at one level. And in this case, instead of providing insulation to bring in the boundaries of the AOI inward, I'm going to provide insulation outward. So in other words, I'm going to extend the AOI boundary a degree beyond the actual element boundary itself. All right. So what does that mean? Let's take a look at yet another example. Oh, before we do that, I'm going to show you some data that we actually captured on this. And what you see is that, and let's say that this is data captured during a pilot test or a validation study. Well, more likely a valid pilot test or a pre-test. Here we see that because of the structure of this particular element, fixations are really central. There isn't much stray to the edges because there really isn't anything at the edges. So the design of AOIs for this particular elements is rational. It makes sense. Likewise, the design of the AOI, this proposed border, for this particular element makes sense as people look at the badge element and the click to buy call to action. There may be some normal eye movement that brings it really quite out to the edge and potentially beyond the edge of the element itself. And if we're interested in something like totalizing the total looking time on this element, then we want to extend it within reason beyond the boundaries of that element. Right? So clearly we wouldn't want it to go so far as to capture stuff down here, but anything that is reasonably looking in this region we would want to capture.
Now let's take a look at another example that we're going to take a little bit further and lead into a discussion of the effect of AOI design choice on the resulting metrics. So let's take a look at this website. It's got a bit more stuff on it, and we are interested in the area down here, the useful links. So there you go. And we collected some pilot data, and it generally looks like this. So let's take it a step further. We're going to dig into this a little bit more and see how we can design the AOIs to explore the elements in the useful links panel here and further explore what could happen to the metrics if we take one route or another relative to AOI design.
Okay, so let's blow this up a little bit. Again, we're interested in the useful links. And how would we set up the AOIs for our analysis, given the data that we've captured in our pilot study? Well, we could set up selective AOIs. So you see here, selective-rate, videos and contests. And let's go ahead and set up another set of sensitive rate AOI. So you can see it's extended quite a bit beyond the selective AOIs. And in this case, because the elements are very, very close together, we do not have the latitude to inject a degree of visual insulation. Sometimes you're just going to be in that situation. You have to deal with what you have. So let's proceed. For this simple example, we're going to focus on a couple of metrics: total fixation duration, fixation count, and visit count. Could be any of these metrics, but I selected these to really highlight the difference that you could see when you bias your areas of interest for selective versus sensitive analysis.
Now let's take a look at the effect of AOI design choice on the resulting metrics. And in this example, we're going to, again, focus on the contest rate and videos AOIs, and initially here, the total fixation duration metric, and the selective forms, which were slightly smaller, and the sensitive forms of the AOIs for these different areas. Now, in the worst case, or in the most dangerous case, you can actually make data disappear or appear, depending on the size of the AOIs, and that certainly could be misleading. In a more subtle situation, you could have a reduction in something that is a durational based measure, such as total fixation duration, where there is data in both of these cells, in both of these sets of AOIs, both the selective and the sensitive. However, you go from 0.35 to 0.24 seconds of total dwell time, and that could affect the findings of your study. Let's take a look at just one more example. We'll go ahead and look at the visit count metric. And same as before, I've set it up with the selective set of AOIs and the sensitive set of AOIs. And just like in the total fixation duration example, you see both missing data and changed data. The missing data is a problem for a count metric because it says basically that there was no looking. And the subtle situation here in terms of the rate and video AOIs for these two recordings would result in dropping of the visit count. So even though it does register a visit count, it's not registering all of them, presumably because one of the two visits took place close enough to the AOI where it's lumped as a single visit, or goes around the outside of the AOI such that it doesn't actually penetrate the smaller or narrower selective AOI. So you can see this is an illustration, a simple one, of how your results can be potentially significantly altered simply by choice of the AOIs in setting them up with a bias towards being selective or sensitive.
So how could this make a difference? How could this make a difference your selection between selective biased and sensitive biased AOIs? Well, what could happen is that for studies involving interest or engagement, where the important metrics might be something like number of fixations or total fixation, duration, or dwell time, you could get an underestimation of the actual interest or engagement. Noticeability or salience. So if the metrics are percent of subjects fixating on an AOI and time to first fixation, if there are no counted fixations in the AOI, you could get quite a strong drop in the percentage fixating, and of course there would be no time to first fixation then. So you could quite significantly affect noticeability and salience measures. And for expertise and efficiency, which might revolve around fixation, duration, distribution, the shape and the characteristics of the duration distribution could be significantly altered by your choice of AOIs.
And that brings us to the end of our webinar. So let's take a moment to review what we've gone over. Eye tracking is visual. Yes, of course it is. And what we learned today was a way of thinking about an approach to eye tracking centered around three spaces for three Ds. And those Ds are the design stage, considerations of the display, and description or analysis. And those three spaces correspond to the abstract world of pixel space for design, the concrete world of screen spacing for the rendering of your stimuli and images, and angular space, which is the space wherein we describe and report eye tracking findings. So I hope that you find some value in this way of conceptualizing eye tracking, because what it is intended to do is to help you work comfortably in between these three spaces and among these three spaces, so that you can design your stimulus properly and figure out how to scale it and display it properly, and also be attentive to the considerations on the analysis end in terms of both setting up the AOIs as well as describing the results of the data. So in total, there are really three things to align in your methods. The first is to be attentive to the task demands. In other words, what are we asking the subject to do? The second is to be mindful of the human visual system characteristics, and this has to do with the decline of visual acuity as we move off axis from the central portion of our visual field as relates to the fovea. and also to be attentive to the analytical goals. What sort of statistics, metrics, or analysis, what sort of inferences, judgments, or comparisons we're going to make. And in doing so, we want to take a mindful approach to design of stimuli and areas of interest, balancing the need for selectivity, which is to include the data that we want, and sensitivity, which is to include the maximum amount of data that could be applicable to an area of looking. So balancing selectivity and sensitivity, as we saw in the preceding examples, can have quite a significant effect potentially on the findings. Very good. Now, for those of you who are viewing this webinar live, we're going to stay on the line for 10 or 15 minutes or so to address some of the questions that have been sent in via the chat function. For anybody who's viewing this asynchronously or on the Tobii YouTube channel, if you have questions about what you learned here today in regards to screen, image, and visual spaces and sizing of stimuli and AOIs, please don't hesitate to send an email to knowledgeservices@tobii.com. If you'd like some more information about Tobii eye tracking systems, both products and services, go ahead and send an email to sales.us@tobii.com. And if you'd like to play with Tobii Studio and to explore some of the features there, and you don't own an eye tracking system yet, please go to the bit.ly/Tobii Studio URL down there at the bottom and download a free trial with a sample project that's already got some data in it. So on that note, thank you very much for attending this webinar. I hope it's been useful, and happy eye tracking.